Right, so how many of you have written parallel code? Okay, I'm going to ask that again. How many of you have written parallel code? Those who haven't put your hand up, put your hand up. Put your hand up if you haven't put your hand up. Because you have. Everybody has written parallel code. Right? Because most of the time, well, all of the time when you're writing code, it's running in parallel. And up to now, we've been very fortunate because the code that we've been writing has been running in parallel without us really having to do anything for it. We've had pipelining and structure level parallelism, and up to now, we haven't really had to pay that much attention because the hardware has been bailing us out. We've been getting faster and faster chips. But there's only so much that we can get with the hardware. Well, maybe they'll make another big breakthrough, but at some point we need to look at solving the problem with software, actually doing some parallelization ourselves. Now, I want to talk about an aspect of parallelism within Java called the ManagedBlocker. It's related to fork join, to the fork join framework. And I did a CPU graph on my little laptop here. It's an i7 Pentium. It's got 4 cores, so it's 4 real cores, and then 8 hardware threads. Because it's got 8 hardware threads, Java, or the operating system actually says that it's got 8 cores. It doesn't really have 8 cores. It's got 4 cores, but hardware threads. So you can see in this graph that the cores have a fair amount of black at the beginning. Once the process starts going, then we have lots of green. Now we want to have green. Green is good. Red is bad. There's not a lot of red, just a tiny bit of red, which is great. We don't want to have too much red. Black is also not that good because it means that we're not fully utilizing our available hardware. And we want to try to calculate some large number, and by having a lot of black at the beginning, it means that we're not fully utilizing. Now, what it did was, this was done with fork join, and I'll show you exactly how I got to this. By introducing the ManagedBlocker, I was able to increase utilization of my available hardware, and it started looking like this. So instead of having the black at the beginning, we now have very little black at the beginning, and it completed 8% faster. So an 8% improvement in performance and utilization of my available hardware. Now, we're going to use the example of Fibonacci, which I'm sure you're all familiar with. It's a very easy mathematical sequence, easy to understand. F of 0 equals 0, f of 1 equals 1, f of n is equal to the previous 2 numbers added together. Now, the numbers get large very quickly, and this is what they had in Australia when the rabbits started breeding without natural predators. They just, children had more children and so on, and they had very, very large numbers of rabbits. And if you implement this as a simple recursive method like this, you can see that the Java code looks very similar to the maths. And if you're a mathematician, you say, well, we're done now. We've written the method, we can go home. But if you try and run this, you'll notice that the performance is beyond dismal. It is absolutely terrible. The computational time complexity of this algorithm is in fact itself a Fibonacci series. So it's basically exponential time complexity. Not exactly, but pretty close to that. Now, interestingly is this algorithm, almost exactly like that, is found in the JDK Java docs. That's why I don't read comments, because documentation doesn't always contain very useful ideas. But this means that if you were to parallelize this, you'd not be able to get very much improvement in your performance because complexity is so bad. This is another algorithm. This is an iterative algorithm. I'm going from 0 up to n, and all I need is to remember the previous 2 numbers. I'm not remembering all the previous ones. I'm not working it out over and over again. And now Fibonacci 1 billion is calculated in 1.7 seconds. But the number overflows around about Fibonacci 70 or 80 or around about there somewhere. So the answer is not correct, but it's fast. So that's great. Not very useful. Now, we could use big integer to make sure the numbers are correct, and so we don't overflow, but the add function in big integer is also linear. So you've got a linear function multiplied, the linear algorithm of the loop from 0 up to n, multiplied by the linear cost of the add inside big integer, and you get a quadratic function. Now, you can work out fairly large numbers, probably 10,000, maybe 100,000, perhaps even 1 million. But you're not going to get to 1 billion. That is 1 billion times 1 billion. It's just too big. It'll take too long to work out. The next one is something called Dijkstra's sum of squares. Now, this is not the best formula. There are even better ones than this, but it's pretty good and it's quite easy to understand. It's basically, if it's an odd number, there's one calculation of adding squares together, and if it's even, then there's a slightly different with the multiply by 2 and some other magic to get to the correct answer. Now, the complexity of the function is logarithmic, so it's like a binary search through a tree. At every point, you're dividing the space by 2. So this is a very nice little function. In previous versions of Java, Java 7 and before that, the multiply inside big integer was also quadratic, so order n squared. And so again, you wouldn't be able to calculate this within our lifetimes, probably, for example, Fibonacci 1 billion. It's just the numbers get too large. In Java 8, they changed that. I'm not sure why, because I don't know how many people actually wanted to do this. And they changed it to have 3 different multiplications depending on how big the number is. Now, you probably know from your studies or experience that a lower complexity doesn't necessarily mean it's going to be faster, because you also, in reality, have to look at the setup cost of your calculation. And so if the number is quite small, then it doesn't pay, the setup cost doesn't pay to use Cook or Karatsuba. In that case, they're going to just use the basic order n squared that we've always had in Java. The order n squared is like your school mathematics multiplications in junior school, where they try and make you do all these silly calculations. And if the number is slightly bigger, then they take Karatsuba, which has order n to the power of 1.585. And there's a big difference between 1.585 and 2. It's a very, very big difference. You can plot it on a graph. You'll notice they deviate very quickly. And if the object's even bigger, the number's even bigger, they use a 3-way Cook, which is more expensive to set up, but the complexity is lower. So you start winning after some size has been achieved. Now, the big integer is single-threaded. So that's something which we'll fix a bit later. We'll do some hacking and change it, make our own big integer multiply method. So the first step we need to do to solve this is to implement this using big integer. Unfortunately, we don't have operator overloading in Java, so we have to do this a little bit by ourselves. And here's what we'll do. Oh, by the way, what I'm going to do is I've got a GitHub repository. I was going to say a suppository, but that's not the right word for it. Git status. And every time I do a demo, I'm going to commit it. So if I forget to commit, please remind me, Andre, you're responsible for that. If Andre doesn't remind me, then you must complain to him afterwards, please. So just remind me afterwards to commit it every time I do a demo. So the first bit is we're going to implement this using the Dijkstra sum of squares. And if I run this at the moment, for example, Fibonacci 1000, I did an estimate, and I estimated that with the current algorithm, Fibonacci 1000 would take approximately 10 to the power of 200 years to complete. Now, that's just this estimate, because none of the atoms that are currently in the universe will be around at that time. You know what I mean? Things are going to be very different in 10 to the 200 years. and I've only got 35 minutes left. So what we're going to do is we're going to change this algorithm to use the actual sum of squares. It's going to look like this. We're going to have, instead of doing it like this, we're going to say int half equals n plus 1 divided by 2. If n is an odd number, we're going to say return, we need to also say big integer f naught equals f of half minus 1, and f of 1 will be f of half. Then if n is an odd number, I'm going to say return square of f naught. Now, there is a square function inside big integer, but it's not public, so we can't call that. But we can just multiply it by ourselves, and big integer is smart enough to realize it's a square. Add f1 dot multiply f1, like so. Else, return f naught shift left by 1, and then we're going to say add f1 and multiply with f1. So this is the result should be the same as before, except that this is going to be hopefully correct. Right, and a lot faster, hopefully too. So let's run this and see how this compares, if it actually runs. So it now finishes Fibonacci 1000 in 3 milliseconds as opposed to 10 to the 200 years. So we haven't done some improvements. Let's do the entire test suite, and we'll see how long it takes to run Fibonacci 100 million. Now the 10 million and the 1 million are fairly fast. The 100 million still takes a bit of time. Now, the 100 million, we're going to, at the moment, it's going to be, let's see how long it takes. Let's just run for it. Now, I print out the GC just to make sure that there are no full GCs happening whilst we're running. And once it's done, we'll take that time and we'll make a note of it. It's about a minute or so. All right, so the first run was 46 seconds. That's my first run. So that's not so bad. So this is my demo 1, is that. So let's quickly commit that. Say demo 1. So 47 seconds for demo 1. Now, if you run this, it is running in parallel, but you won't see it. I mean, all the parallelism that's happening is happening on a single core. Right? So you've got your pipeline, all that stuff that's happening. It's like almost coming for free to us. But what you'll notice that it is only running on one core. So if you take top, you'll notice that Java's only running 100%. Now, it was at 200% just now, but that could be your hotspot profiler, and it could be your garbage collector running at the same time. So that's why you might go over 100%. But generally, it's just running on a single core. All right. Now, the next demo that we want to do is to improve this a bit and to parallelize the actual algorithm itself as well. So instead of having F1 and F0 and F1 being calculated sequentially, we take F0 and we put it into a recursive task, and then we execute that, we fork that, and afterwards we join that together again. So the idea is to use multiple threads, possibly, depending on how many hardware threads you've got available inside your system, to compute this in parallel. So, and this is going to use the common fork join pool. Because I'm not explicitly specifying a pool, it's going to just default to the common pool. All right, so let's try that. And so recursive task of big integer if naught task equals new recursive task. And the code here is moved into the compute function. We then say if naught task.fork, and afterwards we say if naught task.join, like so. So now, before we're running at 46 seconds, I'm now running it on 8 hardware threads, but it's not really 8 cores, it's actually 4 cores. So how fast do you think this will run on 4 cores if it takes 46 seconds on a single core? Pardon? The same? You're a pessimist. Pardon? 2 times faster? Why 2 times faster? Yeah, that's a good comeback. I like that. But did you have any specific reason why you said 2 times faster, or just a guess?
I don't expect it to be more than 4 times faster. I also expect some load on the cores and some scheduling overhead. So I don't expect it to be more than 2 times faster. So I gave you the lowest estimate.
Very good. Let me repeat your answer, because otherwise it won't be on the audio. So the estimate is twice as fast because you have all the cost of scheduling, the cost of context switching, the cost of doing this whole parallelism, right? And it's sort of a very conservative estimate. So it turns out that you're about correct, but your explanation is wrong. Okay, so let's run it and have a look. Come again, logarithmic of? That would be nice, but it's not going to be logarithmic of previous number. Okay, so it runs for a while, and it is about twice as slow. So you're correct. Well done on your pessimism. It's just that your explanation is wrong. Okay, and if I run, I'm going to run this again, and this time I'm going to have top. Okay, I'll just do that again because I didn't do that fast enough. Stop, start, and top. You can see that Java is running at like hundreds of percentage of CPU. Okay, and after a while, it goes down to like 200%. And then after another time, it goes down to 100%. All right? So we have parallelized our algorithm, but that's not where the main bottleneck is. Or that is some of the bottleneck, but not the main one. You see, what we've encountered here is a very common problem that you have when you do recursive decomposition or divide and conquer. At some point, exactly, at some point you've got to merge the results back together again, and that's when you really start paying the cost and paying the price. So the way that we can get around that is by hacking the big integer to be parallel as well. So let me just commit that, demo 2. And so what we'll do is we'll go to big integer, and we're going to change multiply Tomb Cook and square Tomb Cook. We're not going to bother with the multiply Karatsuba and square Karatsuba because those numbers are not that big. Remember that Tomb Cook is, once the numbers get very big, it's going to be using that algorithm. Now, I must confess that I do understand sort of how the Karatsuba algorithm works. You sort of split the number into 2 halves, and you multiply the top and the bottom, and the bottom and the top. But I don't understand how Tomb Cook works. I've got no idea, right? So, and I actually don't want to know. All I know is that it splits it into 5 equal chunks. And then it does some magic that I don't know how it works. But in the end, the result comes out correctly. Now, the point is that I can parallelize this without having a clue about how the algorithm really works. And that's why I'm not going to try and understand it, because otherwise that will spoil that magic trick. All right, let's try the third demo. We're going to parallelize big integer. So we go to big integer, we copy. Oh, by the way, this is a very effective way to increase your lines of code. Control C, if you want to get a bonus. And then go to Java Math. Control V. Bingo, I've just written like 2,000 lines or something. Okay, now, how do I actually use this class, this class? I haven't hacked it yet, I will hack it in a moment. How do I use it? Well, let me just go to the top and put in a little note that I am using it, so I can confirm that I'm actually using it. Come on now, where's the top? There's the top. Static using hacked big integer. Okay. Now when I run it normally, it won't actually show that. It will just run without showing using hacked version. Oh, okay, I made a mistake. I'm supposed to start off, and this is supposed to be /a, right? So normally you wouldn't have a boot class path inside your VM parameters, right? You just have it like this. So normally you wouldn't see hacked big integer, right? But if you do the following, if you say -x boot class path /p, which means prepend, then you can prepend your class to the JDK JVM class. And so you can use your own Java Math rather than the Java Math which is found in the JVM. Okay, so now when you run it, it's going to print out using hacked big integer. Okay. All right, now let's go to our big integer, and we're looking for multiply toomcook. And as I said, I have no clue how it really works. I just know that it does some stuff and ends up with 5 different multiplies. 1, 2, 3, 4, 5. And the rule that I give myself to get this to work as well as possible is to only fork once and then join again before I do my next fork. So I'm not going to fork 5 times and then join 5 times, because that can end up actually constructing too many threads, more threads than we should have in the system. It's really a fork one off, join it, fork another one off. So we're going to do this multiply task, v0 task equals new multiply task with a0, comma b0. Now, this multiply task doesn't exist yet. I'm going to construct it as an inner class of big integer, and it's going to be a, comma b. For some reason, there was used those for maths. Let's make some fields a, b. This is going to say extends recursive task of big integer, and then inside the compute function, we're going to say return a.multiply b. Now, I want to emphasize again that I've got no clue how the actual toomcook works. All I'm doing is I'm creating a separate task to do the multiplication. So I'm going to do the same thing for square, except I just need an a, and I'm going to say return a.square. Square, like that. So square task and multiply task, both are static classes. Okay, let's go back to where we're using it. So I make v0 task, then I say v0 task.fork, which is going to use a common fork join pool. And then once I've done my second multiply and any other work, I'm going to say v0 equals v0 task.join. Right. I'm going to do the same thing for v1. I'm going to say multiply task v1 task equals new multiply task of da1 comma db1 v1 task.fork. And at the end, I'm going to say v1 task.join. Okay, so in this case, I'm actually doing two multiplies for the one fork, but that's okay. It's slightly unbalanced, but it's still going to work well enough, I think. Now, I could also do Karatsuba, but Karatsuba is likely to, it's not going to make a big difference because the numbers are going to be too small. But it would be fairly easy to patch this into Karatsuba as well. Let's do the square tomb cook as well. Here we're going to say square task v naught task equals a naught dot, new square task of a naught, v naught task dot fork. No, why doesn't it? What's complaining about here? Ah, right. Don't need that. Dot fork, and then after I've done, before I do the third square, I'm going to say v naught equals v naught task dot join, and again square task v1 task equals new square task, this time of da1, and fork that. And then at the end, we're going to say v1 task dot join again. All right, so hopefully this is going to get us better performance, right? Hopefully we will now be able to do 4 times faster than the original, right? So we're hoping to get to about 11, 12 seconds with this, if all goes well. Okay. So we run this, and I just want to confirm that it actually is using the right version. Yes, it's using the hack big integer. That's good. And at the end, after some effort, it comes back at 15 seconds. So it's not exactly 4 times. In fact, it's about 3 times faster. But it's also not only twice as fast. Okay. Now, let's have a look at any questions, by the way. We can mix the questions up with the... I write a newsletter. Some of you are subscribed. If you're not subscribed, you can subscribe there. And if you are subscribed, you can say hello and ask questions at that particular special link just for you guys. Anyway, so I'll show that at the end again. Now, thanks, Andre. So Andre gets an award for reminding us to commit. Demo 3. Good. Now, what I want to do, in fact, before I do I'm going to do another change before I do the go to number 4. And that is to actually print out how long each of the multiplications takes. So here we're going to say long time equals system.current time millis, and try and finally time equals system.current time millis minus time, and print out time. Now this is not really going to work. I'm just warning you in case you think it's going to work. It won't actually work very well because system current time millis is a system call. So if you call it all the time, it's going to slow down our algorithm quite substantially. So you'll see now that the output is going to be like, okay, right. So it's going to be very busy. Even if we say if time is bigger than 50, it's still going to take far too long to actually complete. Right. So what we're going to do instead is we're going to change this and say if n is bigger than, let's make it 10,000, then call system current time millis, otherwise just call it naught. And the same here, if n is bigger than 10,000, then call that, otherwise set it to naught. And now you can see how long each of the different things takes. Now, of course, 25 million will include all the other numbers that worked out to get to 25 million. So that's why the numbers are bigger. But you might notice something else here. Do you notice anything? Pardon? I'm working out the same thing over and over again. Okay? And it's the nature of the algorithm, because we are doing this, but we're going, two numbers which are almost exactly the same. And so there's a very high probability of actually having to work out the same number repeatedly. And so that gets us to the next point, and we just commit that because that's actually quite a nice commit, demo 3 with timing. This gets us to the next point, which is you could also cache the results to avoid having to work it out over and over again. Now, you have to be very careful because we don't want to cause a memory leak. We don't use a static cache. We don't use a static map because a static map wouldn't have an easy way of being collected. All right. And what we'll do is we'll do this. We'll make a second method, which takes as a parameter map of integer, comma, big integer, cache. And we're going to make a cache up here, big integer. It has to be thread safe because it's going to be used from multiple threads. So it's going to be integer, comma, big integer. Cache equals new, wrong way around, sorry. Map equals new concurrent hash map. And then I'm going to seed it, put 0, 0, and 1, 1. And then I'm going to return f n, cache. Now, a mistake that I've often made when doing this type of code is to forget to change all the places where I called f, especially if you do method overloading. So a simple trick is to change this name, and then it shows you where you need to add the cache. I'm sure you've done something similar. Okay, there we go. And then I change it back. Now, I don't need this beginning statement, but I do need to do this. I need to say big integer result equals cache.get n. If results is null, then I want to work it out. Only then. So I'm going to say results equals and results equals. I'm going to put it into the map over here. Cache.put n, result, and then return result. Okay. So this is how you can do it. And now I'm only going to work out each number a single time. Right? Wrong. Again, the nature of the algorithm gives you the probability, a very high probability, that you will actually want to work out the same number at the same time from multiple threads. But we do sometimes get to win, and we've managed to get our time down to 10 seconds. So we have managed to achieve something. All right. Now, this is demo 4. Before I go on, is there any better way that I could do this over here? The cache.get, and if result is null, then computer if absent sounds like a good idea. Put if absent, I'll show you one way of doing it with a special mechanism, but compute if absent looks like a very good idea to use here. Now, let's, pardon? Yes, I'm going to commit that. Thank you very much. So let's do compute if absent here. So we could say return cache.compute if absent, n comma key, and then you can just do this. You can say return. You don't have to do cache.put, and you can just do like that. So who thinks this is better? Encoding style. Who thinks this is better encoding style? Who thinks this is worse? Why do you think it's worse, Andre?
Because it is very hard to test.
Hard to test, okay.
Very hard to understand.
Hard to understand? No, it's not. You completely have absent. It's a function. That's easy to understand. No, you're wrong there. Sorry. Any good reasons why it's bad? Yeah, the lambda is a bit too long. I do agree with that. Yes. That's a good point. Let's run it and see if it performs the same. And we've introduced a live lock, infinite loop, into our system. You see, something they don't really tell you, I mean, you can figure it out because it's kind of obvious if you really think about it deeply, but I didn't think of it when I started using it, is that computative absent is not allowed to modify the structure of the map. That's sort of an implicit condition, which I don't actually say, but you're not allowed to do that. They call it a recursive update. This is a recursive update of the map. If you try to do that, it just hangs up. So you can't use it. Even if you like it, if you don't like it, either case, you can't use it here. So we're going to do, how do you do this? Get stash. There we go. Back to where we were. Brilliant. Okay, so we're back to where we were with cache.get. So we do want to do something like computative absent, but we can't use computative absent because that doesn't allow us to change the structure of the map. Okay, let's have a look at another mechanism we could use. And that is to, instead of using get and put, we could use put if absent. Now, there's nothing wrong with put if absent. That works quite nicely. You see, computative absent is trying to verify, or it's trying to guarantee that the calculation is only called a single time. Whereas with put if absent, there's no such guarantee. So what we're going to do is we're going to put a special type of big integer into the map. And if we find that integer, then we know that somebody else is busy working on it. If we don't, then we can start working on it. So put if absent would return either null, or the placeholder, or the actual value. So let's do this. The first thing we're going to do is to make a big private void, final big integer reserved equals value of minus 1,000, so just some number which is negative, so we can see if we looked at it, we knew it was a reserve value. And then instead of saying get, we're going to say put if absent n comma reserved. We're also going to use the reserved as a lock. So we're going to say here synchronized reserved cache.put, and afterwards reserved.notify all to wake anybody up who might be waiting on it. So the first if is if it's null. That's the first case. That means we were the first to put reserved into the map. We won the race. We're going to the calculation. The next if will be else if result is reserved. That means that somebody else put it in before us, and we now are going to wait for them to finish. We're going to say synchronized on reserved, and we're going to say while results equals cache.getN is equal to reserved, we wait. So we wait until it's not equal to reserved. And around this whole thing, we're going to do try catch. And if we get interrupted, we're going to just throw a new cancellation exception. Interrupted. Right. So I've got a wait and I've got a notify. And this means that now I should only calculate every number a single time. And if you look at the output, you can see that that's exactly what's happening. Every number is only calculated once, and we've got a better performance too. 7.4 seconds. That's a nice improvement. This is our demo 5. So we're attacking this problem from lots of different angles to try and get the best performance. Now, when we run the code, at the beginning, if you take a few thread dumps, at the beginning, you'll notice that that at the beginning of the run of the 100 million, most of the threads are waiting. Waiting, 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 waiting. In fact, here's only one thread is actually working. It's like one thread is doing some square, and the rest is just sitting around waiting. And so that, of course, is also not ideal. And that's basically where this diagram came from at the beginning, that at the beginning, it's there's a lot of black. Once the algorithm, once we have more calculations in play, the more different calculations in play, we don't have threads waiting for each other, and everything's good. But in the beginning, we have this problem. So this comes to the demo 6, which is the ManagedBlocker. Now, the ManagedBlocker is a way in which we can have blocking operations that are compatible with the common fork join pool, and in fact, with fork join. There are two classes at the moment that use ManagedBlocker. The phaser, Java 7 phaser, which is a replacement for countdown latch and for cyclic barrier. And then there's also completable future is another class, Java 8 class, which internally uses ManagedBlocker to keep the parallelism high. And basically, whenever you would block, whenever you would wait, you are allowing the fork join pool to perhaps create another thread to keep the parallelism at the same level. When you construct a fork join pool, you don't specify the maximum number of threads. You specify the desired parallelism. That's what you specify. You don't specify the number of threads. And so the desired parallelism is basically the number of active threads. So how many threads should be running at the same time? Now, fork join pool is mostly used for CPU-intensive tasks. That's why your parallel streams use fork join pool. They should be used for CPU-intensive tasks, not for IO-intensive tasks. Okay, so the fork join pool, if you do it, if you block together with the ManagedBlocker, it allows the parallelism to stay high as well. Okay, let's try and add that. This is actually probably the easiest of all the examples. We take this waiting code over here, and this is going to become part of the ManagedBlocker. So we're going to make it inside here a private class reserved Fibonacci blocker, for example, implements the ManagedBlocker interface, which is inside fork join pool. It's got two methods, block and is releasable. And block basically becomes this. It becomes the same code as before. So the code, I've moved it, I've copied it from where I waited before down into the block. And the is releasable is basically your condition predicate, which is this thing over here, right? So let's negate that, and we're going to take this code out of here and put that into is releasable. So my block is actually complete. I don't need to do anything else for the block. The is releasable is the condition predicate that I was using to wait. And I need to have a big integer result, and I need to have a private, let's copy the cache and the int n from up here. Let's put that in here. Private final. And we did, of course, a constructor. So now I've written a complete managed blocker. It's basically taking my waiting code and it puts it into the block method. Then the only thing I need to still change is over here where I do my synchronize, and I'm now going to say my reserved Fibonacci blocker equals new blocker with the n and the cache. Then I'm going to say fork join pool dot manage block on the blocker, and then we're going to say results equals blocker dot results, like so. So I'm just replacing the previous wait code with this code. By doing so, I'm now able to use this within the fork join pool without causing myself major headaches. Okay, let's run it, and I'm just warning you that I did this demo a few times. It didn't actually run fast, it ran slower, so hopefully today it's going to behave itself. And please be faster. Nah, it's not faster. You see, the problem with doing the demo is that for small results, it is very, very slightly faster, but for small results, for small numbers of Fibonacci, you don't actually see a big difference because at the beginning there's not a large time of black. If you take a bigger number like 250 million or a billion, you'll see a much bigger result, but it'll take too long to run for the demo. So we'll be spending most of the time just waiting for the demos to run. So you can try it out with bigger numbers, you'll see a bigger difference. And we'll quickly commit that as well. Demo 6. Now, I've got a seventh demo, which I'm not going to code. You're going to code that, right? That's your job. I do have a solution for it, and I'll give you some clues. So what you'll need to make this work with completable future is you'll need to use my hacked big integer, which you can get from a GitHub repository. Just search for in Riga on my list of repositories, you'll find it. You'll need completable future. You'll need to use, well, I would recommend you use the method then accept both async and the method complete. And you can, by doing that, you can actually get rid of the managed blocker because it's done automatically for you inside the completable future, and you can get rid of the reserved caching scheme. And so the idea is the following: that instead of having a cache that contains big integers, you're going to have a cache that's going to contain completable futures. Your main thread is going to set up the entire cache of calculations, and then in the end, you're going to join the values and give the result back. Now, something you can try out with larger numbers. So don't just try 100 million, because 100 million completes too quickly. Try it out with bigger values like 1 billion to see how that performs. But also try out what happens if you try to disable the fork join pool. If you say common parallelism equals 0, see how that performs. And if you're interested, send me your answers here on that link, tinyurl.com, Riga17. Also, if you want to subscribe to my newsletter or say hello, you're more welcome to do so. Do you have any questions? We've got a few, about 7 minutes left for questions, I believe.
Have you tried to do this with Java file streams?
Okay, so the question is, have I done this with parallel streams? I wouldn't know how to. If you can figure that out, I'd be very interested to see. I sort of thought of doing it with a split iterator, But the split rate is really just it's ideally used for iterating and splitting at the same time. So for parallel processing of collections. It's not really for parallelization of algorithms. So I myself, I don't know how to, I wouldn't know how to do it. So if you figure out a solution, please send it to me. I'd be very interested to see it. And yeah. Any other questions?
What is the answer for first task?
The answer for the first task, what do you think? So we had so those of you who were here 2 years ago, I had a chat to Ted Neward last week. Do you remember Ted Neward's incident? Yeah, you do. So he recommended I do some shopping before I come here. And I was looking for some shopping, but I didn't actually get a chance to get what I needed. And luckily I didn't need it after all. So anyway, let's look at the print line. Print line fun. What is the output?
Numbers 0, 4, 1, 3, 2. Random.
Random? Why random? Because it's a parallel stream or why? Okay, maybe. So, if you go to my GitHub repository, which is Kabutz, right? GitHub Kabutz, you'll find all of these files, and you can try it out. Any more questions? If not, then I'm going to let you go for lunch quickly before the long queues start. You've got 3 minutes to get your place.